Man, normally there's more people at least in the waiting room at this point. Okay. We'll do this thing just in case. Okay. Yeah. All right. 9:45. Let's let the rest of these people in and get started. Lord, thank you for bringing us together this morning. Thank you for everything that you've done for us. Thank you for all the blessings that you've given us. I pray that you would help us to just finish out the next week strongly. Help us to get everything done that we need to and to have a nice, relaxing few weeks with family and friends over the holidays. In your name we pray. Amen. Okay. Okay. So, let some more people in. There's some more people. We'll give them a second. It's the last lecture, guys. It's the last lecture of of, of the year, right? We made it almost 15 weeks. So let's get started, right? So we'll recap a little bit. Okay, so here's the thing. Another perfect lesson, no issues, right? So that's great. But in case you guys did have questions, right? We're going to talk about some things, right? So what have we been talking about the past 3 weeks? Let's quickly recap the entirety of what's going to be considered fair game material for this exam, right? I didn't make a specific slide for it, but we can talk about it really quick. This is all homework 6 and 7, right? That's frequency response. So how do we find the steady state frequency response of a system? It's about reading Bode diagrams, right? Transmissibility, resonance, all of those things, right? So first off, modeling. We still need to know how to model systems, right? There's a couple of questions in your homework where you had to model a system. That's still a skill that I hope that you've retained since the last time you've taken the exam. If you're not feeling confident about your modeling skills, that's fine. Please come to office hours and I can try to help you out as best we can, right? Second, beyond modeling, right? We start off with frequency response. It turns out that all you need to characterize the frequency response of a system just grabbing my markers. Sorry, hold on. All right, and let me do this. Right, turns out that all you need. Oh, not okay. Well, that's not gonna work. That's fine. All right, so it turns out that all you need to characterize the frequency response of a system, right, is what? You need magnitude and phase. Why? Because the steady state equation, and that's, hold up, trying to make this so that the people can actually in the classroom can see what I'm writing down. There we go. Steady state of a system is the magnitude of the sinusoidal transfer function times the original amplitude the original amplitude of our system times the sine of omega t plus phi. Now, when we look at this equation, right, we need to know this, right? This is just the original amplitude of our system that you know, right? We'll know this because we'll be given, right? We will be given a frequency at which our input is operating, right? Typically, we're given like 5 sine 20t, right? This is an input of sine 520t or something like that. And this omega is in radians per second, right? So the things that we need to figure out to get our steady state response is the magnitude of our sinusoidal transfer function and the phase, right? So how do we calculate magnitude and phase, right? Well, we did a big thing with it last time, right? But I want you to imagine that we have these things on the real and imaginary axis, right? We're in the S-plane. And here is this is a vector that describes g of j omega. Okay? That is a vector that describes that. And this will be phi radians from the real axis, right? That's what it will be. Okay. How do we decompose a vector into magnitude and phase, right? Well, this is what we're asking is how do you find the magnitude of this vector, right? What is the, well, if you know this distance, right, the imaginary distance, and you know the real distance, right, finding the magnitude of the resultant is just Pythagorean theorem. Finding this angle, if I know the imaginary and the real components, is using the tan inverse to find that, right? So it boils down to trig. We did a more extensive example, right, in class last time, where we had 3 different things, right, drawn on our plot. Why? Because remember, g of j omega can be written in the polar form as this, right? This is equivalent, right, because we know that the transfer function has to be y of j omega over u of j omega. We can write the equivalent expression in terms of u and j, or u and y, excuse me. Notice that my phis here are different. They have to be different. I mean, they probably will be. There's nothing stating exclusively that they have to be. Or what if they were the same? Well, if they were the same, there'd be no phase shift, right? Right? So we have this, right? If we equate, right, I can draw these too, right? This is what we did last class at the beginning. But I can draw these on my plot, right? I can say, well, here's, this is y of j omega, and here's u of j omega, right? So I can rewrite these, I can draw these, and I can calculate the magnitude and the phase of these 2 vectors the same way, right? The same way. And then how would you combine them? Well, because of the polar form here, right? Because we have e to the j phi 1 divided by e to the j phi 2, this is just phi 1 minus phi 2, right? Because when you divide exponents, you're just subtracting them, right? Laws of exponents. Yeah. So that's magnitude and phase, right? And the reason we introduce magnitude and phase is, yes, it's nice that we can solve this equation, right? That's nice that we can figure out what the steady state response of a system to a sinusoidal input is. That is a nice thing. But the real reason that we want to talk about magnitude and phase is so that we can construct Bode diagrams, right? Because Bode diagrams take the general form of our magnitude and phase equations and sweep it through all of the frequencies, right? And so we can tell how a system will behave at a variety of frequencies, right? So if you were given a Bode diagram, you would hopefully be able to pick off the magnitude from the magnitude plot at a specific frequency, right? So we should be able to get this. And hopefully you would get the phase off the phase diagram, right? Because why? Because it's just the phase in degrees, right? So what do you need to be able to go into there? Well, you need to know what your operating frequency is, right? Now, when we're designing things in the real world, right, like an automobile, right? What's going on with that, right? Is there one operating frequency that we're at? No, we're designing for a range of operating frequencies, right? We're designing for a range of operating frequencies, right? So use the example again, right? But asphalt, right? Asphalt in your car, the asphalt that you drive over in your car is not uniform, right? It's not uniform. And we need to be able to attenuate all of the high frequency vibrations from that we're going to see from that, even if they're not all operating at, let's say, 1,000 radians per second, which, as a side note, you guys have all seen, this was years ago, they designed that road where if you drive at a certain speed, it will play a song based off of the vibrations and the grooves they put in the road. Same similar principle, right? You can control what the frequency is so you can produce sound, right? Okay, but that's not really helpful here or there, right? So Bode diagrams, right? Very nice and powerful tool. Allow us to tell a lot about a system if we know the range of operating frequencies that we're expecting to see, right? We did a problem last time where we talked about the impulsive response, right? And we could calculate the frequency response of that of the of an impulse response, right? And that all came from the roots, right? Because if you have complex conjugate roots, then you're going to have two operating frequencies, right? Two natural frequencies that are going to control how that system decays. Okay. So that's Bode plots-ish, right? Sticking with the theme of Bode plots, right? Sticking with the theme of Bode plots. Sorry, one second. So sticking with the theme of a Bode plot, right? We've got magnitude and we've got phase. Magnitude is in decibels, right? So how do we get from unitless, which is what we calculate magnitude as, to decibels? How do we get there? How do we get there?
It's 20 log the magnitude of G of J omega.
Correct. There it is, right? 20 log base 10 magnitude of G of J omega, right? So we take the one that we calculated,
If you throw it into a log and you multiply by 20, right? That gets it in decibels. Great, and that's what we plot in the top part, right? So if we wanted to go the reverse direction, right, we would have to solve this equation. And turns out, if we do that, it'd be this, right? G of j omega is equal to 10 to the decibel gain, or the decibel magnitude divided by 20, right? Because I just solved this applying my exponential rules. Right? That's all that I did. Okay. Great. So if we get something from here and we need to bring it back out to do our y steady state equation, right? We've got to convert from decibels. Otherwise, it's gonna be a bad day, right? Phase is in degrees, but the phase that we report in our equation is in radians, right? So we're gonna have to pi over 180 it, right? Or 2 pi over 360. However you can remember it. Bodie diagrams are nice, right? And for first order systems, we have this set of rules for drawing the asymptotes for Bodie diagram. Now, I've said to you on multiple occasions that in the real world, in the wild, nobody is going to say to you, draw this Bodie diagram by hand. Right? That's not how it's going to work. But we like to do it by hand so that we can get a feel for how these systems are supposed to look, we can get an idea of how they're going to react at specific frequencies, right? So for a first order system, we have our rules, right? And the first rule is that given the transfer function, we find the DC gain and we convert that to decibels, and that's our low frequency asymptote. Our low frequency asymptote is DC gain. In this case, right, for the purpose of this illustration, so nobody can see the top there, so let's do this. Right. We'll say that we're starting at 0. So I found out my DC gain was 0, and I draw my low frequency asymptote there. For a first order system, I have to have a corner frequency, right? This is going to be the point at which my low frequency asymptote converges with my high frequency asymptote. My high frequency asymptote, let's talk about that first, is what? Well, it's minus 20 dB per decade. And that starts at omega c, the corner frequency, not to be confused with the cutoff frequency, which we'll talk about in a second. But the corner frequency for a first order system is 1 over tau, right? So the time constant comes back. How do we find the time constant? Well, it's a great question. There's a couple ways that we learned how to find the time constant, right? The first one is look at the roots, and it's 1 over the root, right? The second way is write it in standard form for first order characteristic equation, and then just read it off of your diagram, right? So we have some frequency, let's say it's here, this is 1 over tau, right? And so at that point, where we intersect, and I have my high frequency asymptote there, and this is going to be at minus 20 decibel per decade, right? So every 10 tick marks, it will decrease by 20 decibels. Okay? And if we were going to draw something like this for a first order system, right, you get something that would probably look like that, right? If you were to put this in the MATLAB, you'd probably get a Bodie diagram for magnitude that looks like that. Phase, what about phase? Well, for a simple first order system that has no zeros, which are the ones that we've been looking at, right, for the most part, we start at 0, we end at minus 90, and we cross minus 45 at our corner frequency. And so we have an asymptote that kind of looks like that-ish, right? What about for a second order system? Well, turns out that most of these rules don't change. There's a couple things that change, right? But most of them stay the same, right? So our low frequency asymptote still stays at the you know, the DC gain converted to decibels, right? So let me draw that with this purple marker. So we can have both of them on the same, right? So the purple one, this is gonna be my second order system, right? And so, all right, my high frequency asymptote is actually minus 40 dB per decade, right? Minus 40 dB per decade. And that happens at the corner frequency. But the way that we find the corner frequency for a second order system is different because this is based off of the natural frequency. So for a second order system, the natural frequency is the corner frequency. So let's just say for the sake of argument that this is omega n is equal to omega c, right? So at this point, I get my minus 40 dB per decade asymptote here, right? And if you were to plot this, depending on what zeta is, right, you'll get something. I'm gonna try to do this without junking it up too much. Find a good color. There we go. This will do it. Right. You should get something that kind of looks like that. That has this peak, right? And we'll talk about that peak in a second. What does my phase look like? Well, in this case, we're going to go from 0 to minus 180. We're still going to cross, we're going to cross minus 90 here, right? And the steepness of which we approach and leave the corner frequency is dependent on zeta, right? Dependent on zeta. Depends on my damping ratio. So that's Bode diagram asymptotes for first and second order systems, right? And if you have the asymptote, right, there's no, again, you're not beyond drawing the asymptotes, you're not going to need to draw them, right? But if you were to print out a Bode diagram, the asymptotes would fit, right? Remember, the asymptotes are the envelope that the Bode plot fits around. Right? So what can we do with the Bode plot, right? We said earlier, right, we can pick off our steady state response from the Bode plot given a specific input, right? We can do that. We can also talk about some more interesting things. Bandwidth is one of them, right? And bandwidth is the frequency range over which we have good following, right? Good signal following. Another way of thinking about this is it is the range over which our signal is strong, and once we cross out of that frequency range, we have lost a certain amount of information that may be deemed as vitally important, right? And the typical standard here is a 3 dB degradation, right? So typically, how do we find bandwidth? We go to our DC gain, we subtract 3 dB, right? So in this case, we come down to 3 dB. We come across wherever my Bode plot hits that, that is now my cutoff frequency, which is omega B. Cutoff frequency omega B. And anything that is above that 3 dB line is good for our bandwidth, and anything that's below it, we shouldn't be operating, right? That's how we use bandwidth. Right. We can also talk about resonant frequency, right? What's resonant frequency? Well, resonant frequency is the frequency at which we will have our peak amplitude, right? So in this case, it's probably like right there. It's usually it's around omega n, right? It will never be larger than omega n. At the highest case rate, it will be omega n. When it's omega n, that's problems. And we'll talk about that in a second when we get to transmissibility. But remember a little bit from last class, right? With transmissibility, you end up having if you have zeta of 0, right? You end up having this infinite spike at omega n, right? That's not good. That means that you infinitely amplified your vibration, which is typically a bad thing, at least for mechanical systems. There's an equation that we can talk about with resonant frequency, right? Get rid of this. There's an equation we can talk about with resonant frequency. We can say that omega r is equal to omega n on the square root of 1 minus 2 times zeta squared. That is the resonant frequency equation. And if you know omega n and you know zeta, which you should be able to get from your standard form equation, right? Then you should be able to figure out where omega r is. Also, if you're given a Bode plot, it's typically pretty clear where omega r is, right? Because it's wherever that peak amplitude happens to be. It's important, right? We have alluded to it right now, and we'll talk about it more with transmissibility, right? But typically for mechanical systems, we want to try to minimize the amount of time spent at resonance, right? Typically for mechanical systems, we want to attenuate vibration. We do not want to amplify vibration. Typically. Okay. Everybody good so far? We got any specific questions that have arisen? After this, we're going to go through transmissibility. We'll hit unbalanced rotation. We'll do a case study. And then whatever time is left over, you guys can ask other questions until we're 30 minutes away from the end of class, right? And then we'll do our makeup points. Okay. Does anybody have any questions? Everybody doing all right? Okay. All right, so transmissibility then. Transmissibility. Transmissibility is the measure that we use for describing how a system suppresses vibration, right? A large transmissibility number means that we are going to amplify the vibration that is put in, and a small transmissibility number means that we're going to attenuate it, right? And the bottom line is, right, we came up with this very lengthy equation, right? Came up with this lengthy equation that's in terms of beta and zeta, right? Where beta is my frequency ratio, right? Remember, beta is omega over omega n, where omega is my operating frequency and omega n is just my natural frequency, and zeta is my damping ratio. There is one thing that I want to point out before we actually move on about resonance frequency. I apologize, my brain skipped for a second, right? So here's my magnitude plot, right? And I've got the previous example thing we talked about, right? We had this first order system and we have some second order system, right? They both look like this. Does a first order system have a resonant frequency? No, it doesn't. Is there a case in a second order system when you wouldn't have a resonant frequency? Yeah. Okay. Happens when zeta is 0.707 or larger, right? And it will start to look like it is a first order system, at least in the frequency domain. Okay. Remember, with increasing zeta, this starts to flatten, right? With increasing damping ratio, this peak flattens out, eventually goes away. Okay. So transmissibility, right?
Wait,
Measure by which we can tell how much vibration is either amplified or attenuated in our system, right? And we came up with the big equation for it, but really, transmissibility can be talked about in two fundamental ways. One is the transmission of a displacement through a system, and the other is a transmission of a force through a system, right? And we developed these equations where transmissibility is the amplitude ratio of my transmitted displacement to my input displacement. It is also equal to my transmitted force to my input force, right? These are the amplitude ratios, right? We're talking just about the magnitude of it. It has nothing to do with the operating frequency. It has everything to do with how much force and how much displacement are we giving it, right? These two numbers are equal, right? They have to be equal. You won't have two different transmissibilities for the same system at the same frequency input, right? At the same input. It's just not going to happen. This, though, looks an awful lot like this, because that's what it is, right? If you can calculate the magnitude, you can calculate the transmissibility. If you go to the Bode diagram and you're told that you have a transmissibility limit of a certain amount, right? Find G of j omega, convert it to decibels, right? Or if you're given the transmissibility limit, say it's 2, convert 2 to decibels, go into your Bode diagram, find where that happens. Anything above 2 decibels, we don't want to operate there, right? We've decided that that is not, we don't need to have twice as much vibration as we put in, right? We don't want to operate under those conditions. And so we can limit our design by knowing about transmissibility, right? Recently saw a problem in studying for some professional development stuff, where they give you, remember that chart that we came up with that has the transmissibility on the y-axis and beta on the x-axis, right? For systems that are vibrating, right, we need to understand, and here, let me try to find it and share it, because trying to draw it is a nightmare, honestly. Oh, that should have been, sorry. I think that was here. Let's find out. Yep. There it is.
Doctor, do you have a question?
Yeah, what's up?
So you said the larger the transmissibility, it's being amplified, right?
Yes. Well, all right. So transmissibility larger than 1 means that we are amplifying the amount of vibration in the system, right? Because if you convert that to decibels, you'll have dB greater than 0, right? Transmissibility between 0 and 1 is attenuation, because that's going to give us negative dB. So here's the chart, right? And I actually saw this while studying for a thing, right? So you potentially will see this again at some point, right? And we're told in the question that I was given, you know that your system has a zeta that's half of the critical damping ratio, right? Which means what? Well, it means that it's 1/2, right? Because the critical number is 1. So we know that it's operating at 0.5. So you have to come down to the 0.5 curve, right? And they want to know, where are we going to have this much transmissibility, right? They give you a number and you got to, tell me what frequency I should operate to get a transmissibility of X, right? There's general things that we want to talk about when we see this curve, though, right? General trends for transmissibility, right? The first is we've got this beta is equal to √2 point, right? That's the point right here. And beta is equal to √2. That's kind of our transition point, right? Anything to the right of that, we'll have a negative transmissibility, right? Or will attenuate our vibration. Anything to the left of that, the best we can do is transmissibility of 1. So to the left part of this curve, right, the left part of √2, increasing zeta flattens the curve, right? But, and that's generally what we want, right? So if you know that you're operating with a beta of less than √2, you should try to minimize your damping ratio. If you're operating with a beta of greater than √2, I'm sorry, I said that backwards. You want to maximize your damping ratio to the left. You want to minimize it to the right. Apologize. Now you want to minimize it to the right. Okay. So how does this work for design standards and design principles, right? So when we're designing something, we want to do what? Well, we want to try to see if we can get our beta in the greater than √2 range, right? Because that's automatically helping us out with vibration attenuation. If we can't, then we want to, and we know that beta has to be, right? Because my operating frequency is such that, you know, I can't possibly change the dynamics of my system, right? It's not feasible. So what do? I minimize zeta. Yeah.
So do we want beta as close to √2 as possible, or do we want beta as high as possible?
You want beta to be as large as possible, greater than √2, right? That's the only way that we attenuate these vibrations. Right? If you can't, if part of your system is locked in and you can't change, so how do we change beta, right? Well, you got to change the natural frequency, right? So if you're looking at beta, beta is omega over omega n, right? How do we change the natural frequency? It's the square root of k over m. So you either change the mass or you change the spring constant, right? The overall result that you want is you want to minimize the natural frequency, right? In comparison to your operating frequency, because that's going to increase beta, right? So from a design standpoint, this means that you can pick the spring constant and the mass such that you have a low omega n, right? When compared with your operating frequency. Now, in certain cases, that might not be feasible, right? But if it is, and you can spec for beta being greater than √2, then what you want to do is you want to fiddle with your damping coefficient until zeta comes down as much as possible. Okay? So that's transmissibility, right? What can we do with transmissibility? Well, we go back to the Bode diagram, talk about this a little bit. We can kind of treat it like bandwidth-ish, right? Instead of it being at a fixed point, right, you'll have a transmissibility limit, right? You go find that transmissibility limit on your magnitude, go until you cross your Bode diagram, right? Anything that operates above that, and though you want to stay away from those frequencies, anything that is below that, you want to maintain operation in those frequencies. Now, in real world, right? Real world, you might have to pass through your natural frequency and your resonance point to get to your operating frequency, right? So you're driving your car. The faster you go, the faster the frequency of your input from the road, right? It's directly proportional. So you want to spend the least amount of time near resonance as possible. That's the idea. Okay. Okay. That brings us up pretty much to to where we stopped last time. Right? That pretty much recaps the last few weeks. And we're going to talk about rotating unbalance today. I actually saw an example of rotating unbalance on my way to school today on my commute. Somebody's hubcap was appropriately um, not appropriately centered, and that thing looked like it was going to pop off. Right? A lot of excess vibration there. Right? You guys have any questions specific to anything that we just went over? Anybody doing all right? In that case, here's the things that are due. All right, we've got exam 3 on Thursday, benchmark and presentation due on Sunday or by Sunday. All right, so what's rotating unbalance? We kind of went over this a little bit in class before we left on Thursday last week, but I said we'd cover it again, right? So what is rotational imbalance? Rotational imbalance is exactly what it sounds like, right? You are rotating and your system is not balanced. Now, everything in the real world has some level of rotating unbalance, right? Everything that is a rotational system, right? It's very hard, unless you have very high tolerances, it's very hard to create a perfectly balanced system, right? Some things come very close, but for the most part, right, we accept that there's some, right? We all believe in the second law, and there's something stealing our lunch all the time, right? Okay. The mass center of our object may not be aligned with the center of rotation. And the distance away that our mass center is from the center of rotation is what we define as the eccentricity. Okay? So in the figure here, right, this epsilon, that E, right, okay, hits some point, right? That's from our center of rotation out to M sub U. M sub U here is our mass center of our rotating body, right? And obviously it's rotating with some velocity omega. You can see there's vibration isolation mounts attached to the bottom. So the amount of force that we can say are exerted on our bearings due to this rotational imbalance is given by the equation below, right? Which is F sub r is equal to M sub u epsilon omega squared sine omega t. Okay. So you can see there's a couple of things, right? The farther the distance away we are from our, right, the bigger the eccentricity, the more force that we have transmitted into our, or that we are placing on our vibration mounts, right? Or the larger the mass increases. But what really sends this thing stratospheric is the speed, the rotating speed, right? Omega is squared. So omega is driving the bus. Small changes in omega produce large changes in the bearing forces, right? So we'll go through the derivation, right? So remember, we're interested in two things, right? We're interested in either transmitted force or transmitted displacement, right? Those are typically the two things that we want to characterize. So the definition of force transmissibility, which we talked about earlier, is the amplitude of the transmitted force divided by the amplitude of the input force. But in this case, we're going to say our input force is the bearing force, right? The M sub u epsilon omega squared. And we'll use our normal standard second order equation, right, for a mechanical system. So we can solve it, we can get the transfer function, right? And we pop in our sinusoidal transfer function. So substitute all of your S's for j omega. If you're still using the time domain transfer function, that's fine. All your D's become j omegas, right? Same deal. Notice how this is written, right? This is the way that we've been talking about it, right? But here is the real portion, and here is the imaginary portion, right? Remember, if you're going to find magnitude and phase, combine your real portion first. Don't try to do it as three separate terms. You're going to have a bad day. Okay. Okay, look, there's our transfer function. And, you know, wouldn't you know it, we're going to find the magnitude, right? And if we find the magnitude, we will get this. And that equation should look kind of familiar. It kind of looks like our transmissibility equation, right, that we developed 2 classes ago. So there's our transmissibility equation. So it turns out, right, that the magnitude of x of j omega is just the transmissibility times this ratio of my total mass to my offset mass times epsilon times my eccentricity. But wait, Dr. B, you said we wanted to talk about force transmissibility, right? But you did all this with displacement. It's true, I did say that. How does this all play together, right? Well, the transmitted force is equal K plus BS times X of S. We know what X of S is. We can just solve for it. Right? And we're going to put this as j omega as well, right? We're going to put this into the frequency domain in a second. Right? So we can plug this in. We'll get this bad boy, right? And then force transmissibility, we'll just give it the old transfer function treatment, right? Divide out by f sub t of t, or of s, f sub r of s, I guess. And we perform the same manipulation to get everything in terms of beta and zeta, and there it is, right? So you get our transmissibility, or force transmissibility, as a function of beta and zeta, right? Great. So that means what? That means you need to know zeta and you need to know beta for balance, and you also need to know, well, you need to know epsilon for the positional, right? But not for the force transmissibility, right? Not for that. Okay. Thus ends topic 6, question mark, the final topic. Okay. Do we have any questions before we launch into our case study? It's 10:30. We need to be done by 11:45, right? No.
Just for, I guess, extra study material for the exam, if we give the, I guess, the full, August 6 and 7, the solution available.
So I posted solutions yesterday afternoon. They should be up there
Yeah,
for the mega homework. Are you asking for, you want like the original versions of 6 and 7? Ah, sure. Why not? I'll post those later today. Yeah. Yeah, that's easy. All right. If you don't see them later today, please remind me to it. Apologize if I don't. But yeah, you guys can have those. No problem. All right. What do you want to talk about? before we launch into the exciting world of case study? No? No? Okay. So here's our case study. We're going to use car seat. Not like a kid's car seat, but like an actual seat. This is, all right, for the intents and purposes of this, this is going to be the vibration isolation system seen between your, or in this case, the commercial vehicle's seat, right? And so what do we have? We've got the vibration isolation mounts of the seat that's connected to the floor of the vehicle. And then we've got the seat itself, which is going to have some vibration isolation properties. And then we're going to have the driver sitting on top, right? So the seat has a mass, the driver has a mass, right? Each one of these has its own individual displacement, right? We've got some input displacement of the cabin floor. Okay? So the goal is to analyze the dynamic response of the seat suspension system using the tools that we've developed so far, right? So, you know, first things first, right? We need to make a model. So if we lump all of our masses, right, we've got the driver mass, that interfaces with the seat mass through vibration isolation system, K and B, K2, B2. Then we have the seat mass, which interacts with the floor through K1 and B1. Right? Free body diagram, so we do our inputs and our outputs. We need to write our mathematical truths, and we need to reduce our equation. And in this case, you can do it a couple ways, depending on how you want to set up your Simulink model, because that's where we're going to end up going, right? But I'm going to end up doing it in state space because of the way that I set it up. Do you need to do it in state space? No. You could, if you wanted to, create a transfer function and do it as a transfer function model. But I think from last class, we kind of saw that dealing with a fourth order transfer function is very much fun, and we all love the algebra, but doing it as state space is a little bit cleaner. It's going to be a little bit cleaner. Okay, so free body diagram, right? I'm going to say my input, just so we have it, is, I believe we called it Z0 here, right? Yep, Z0. Z naught of T. And my output is going to be Z1 and Z2, right? So I'm going to have a dual output system. I want to track both the measurements here. Do I need to do something with both of them? No, but I'm going to track both of them as the output. So that's going to affect what? That's going to affect my output equation. That's it. It's not going to affect my state equation. Right. So mass one, right? So let's assume, right, from the bottom, assume we push up. Let's say that that first set is compressed, right? That first set of springs is compressed. That's compressed, right? Then I should be seeing FB1, right? Sorry, I picked the wrong. Did I do that backwards? Yes, I did that backwards. There's an easy fix here. I'm just going to do this. So we'll say that the floor is compressed, and we'll say, right, that the base also moves more, right? So the top's going to be compressed as well. So if we're compressed there, we'll end up with FB2. There we have it. That's, we're also assuming, we're assuming that we start at an equilibrium point, right? So that the mass, right, the weight of the weight is taken up by the initial deflection of the spring. Right, so it cancels itself out. Everybody good? Are we good so far? Yeah. Any questions? No? Just the free body diagram. All right, so since we did our FBD and our inputs and outputs, right? Oh, wrong one. We get to our mathematical truths, right? And so we should have one set for each block. Some of the forces on block 2 should be the mass of block 2 times the displacement of block 2, or the acceleration of block 2, excuse me. Fk2 is equal to K2 Z2 minus Z1. Or sorry, I wrote that backwards too. Z1 minus Z2. And FB2 is B2 C dot 1 minus Z dot 2. Some of the forces on block 1, Z double dot 1. There we go. Okay. So what order is this system? Yep, seeing it. 4. It's fourth order, right? 2 masses, fourth order will give me 2 second order differential equations. So I said I'm going to do this as state space, right? So I'm going to want 2 coupled first order differential equations when we get there. Right? So we're going to do our reduction, right? We're going to come up with our 2 coupled first order differential equations. Then we're going to do our state variables, right? And then we'll set up our state space equation, right? Our state equation and our output equation. Because those are both, we need, remember, if we're going to do this in MATLAB, we need A, B, C, and D. Right? That's the important things that we need to report back to MATLAB. So if I start with mass 1, right, I get what? I get M1 Z double dot 1 is equal to negative K2 Z1 plus K2 Z2 minus B2 Z dot 1 plus B2 Z dot 2 plus K1 Z naught minus K1 Z1 plus B1 Z dot naught minus B1 Z dot 1. Right, so making this an input-output equation, which I like to do, right? But it's not necessary. It's arguably not necessary if going right to state space, right? It's actually beneficial to have it as terms of the double dot, but I'm going to write it out anyway just so we have it. Right, so we'll talk a little bit about it, right? The benefit of doing this in state space, right, is first of all, you don't have to do a combination of these two systems, right? So we don't have to take the Laplace transform. We don't have to then do all the algebra to combine them to get my fourth order equation. I don't have to do any of that, which is nice. Remember though, state space is also robust to any non-zero initial conditions, which you might end up seeing in real life. And any linear combination of outputs that we want, we can find, right? So that's also nice. All right, so if we reduce the second mass, let me get that. Something that looks like that, right? So we've got to set up our state variables. In this case, we already said that it's a fourth order system, so we're expecting to have 4 state variables, right? And remember, the choice of state variable is completely up to you. You can pick whatever you want. However, I do think that I'm of the mindset that for most of the things that we are doing, it is beneficial to think about energy storages, right? How is this system storing energy? It's storing energy through position and velocity, right? And so the position and the velocity of each of the blocks are good places for us to have our state variables. So state variables, right? So I'll have x1 that I'm going to say is equal to z1. I'll have x2 is equal to z dot 1. X3 is equal to z2, and x4 is equal to z dot 2. Right, remember, we also want the first derivative with respect to time of our variables. My input, well, I've got 2 inputs actually. I've got z naught and I've got z dot naught, right? I have the position and the velocity are being input, right? I need to know both of those as my input, and we said that y1 is equal to z1, which is x1, and y2 is equal to z2, which is x3. In reality, what would we really want to pull out of this, right? Just the position of the seat and the driver? We probably don't really care about the position of the seat. But what we do care about is the acceleration of the driver, right? Why? Well, anybody, I don't think anybody here is in a crash test group for senior design. Like, Ronyo? Well, all right. So I stand corrected. But when you're talking about crash test dummies, right, and crashing in general, we're talking about the rate of change that acceleration sees, right? Or as is colloquially known, jerk, right? You want to know what is the rate of change in that acceleration. I had a professor once who told me that it's not the velocity that causes injury, right? It's sudden changes in acceleration, which are harmful, right? It's not the fact that you're accelerating, it's that that acceleration is changing wildly and quickly. That's what's going to cause injury, right? That's what you really want to see here, right? Because the last thing you want is for the seat to accelerate rapidly as it's vibrating, and you know you end up with compression fractures in your spine because you're rapidly compressing and extending your spinal column. Okay, anyway, we're gonna do, so you know what? Why don't we throw that in there? I'll throw that in there too. Seems like a good idea. And now's everybody's favorite part, where you would go back and you would plug in all of your state variables, right, to your equations, and then you would make your matrices. Yes? I'm just going to show you the matrix right now. And so remember, the process is what? We go back to the equations you had on the previous slide. We solve them for the highest order derivative, right? You plug in the state variables that you chose, right? Then what happens? Well, in this case, just setting it up. I've got this. I hope I gave myself enough room. All right, so first off, x dot 1 is equal to x dot 2, right? Because x dot 1 is z dot 1, and that's equal to x2, which is also z dot 1. So 1, 0, 0, 0, or 0, 1, 0, 0. Can't even say things correctly today, guys. It's great Monday. I'm actually going to give myself a little bit more room to fill this out. That's negative quantity K1 plus K2 over M, negative B1 plus B2 over M, K2 over M. This should be M1, by the way, sorry. K2 over M1 and B2 over M1. I realize that that is scrunched up and not nice looking. I apologize. Did not estimate appropriately. Remember, the equation is AX plus BU. Right? X dot is equal to AX plus BU. Right? X3 is equal to X4. And then we get this. Which of these equations will have u in it? Well, not the first and the third, because that's just x dot 1 is equal to x2 and x dot 3 is equal to x4. X dot 4 isn't going to, right? Because why? Because x dot 4 has to do with the mass 2, which is the seat, which is not directly, there's no direct input of z0 or z dot 0. So it's just here, k1 over m1, b1 over m1. Okay. State equation. X dot is equal to AX plus B U. Output equation. Y is equal to CX plus D. So Y1 is equal to Z1 is equal to X1. So if Y1 is equal to X1, right? If I were to multiply, let's do the linear combination here, right? So you have 1 times X1 plus 0 X2 plus 0 X3 plus 0 X4 plus 0 U1 plus 0 U2 gives me that Y1 is equal to X1. Y2 was equal to Z2, which is equal to X2. And Y3 was equal to X dot 4, which is just the same as the final row in our previous equation. And there we are. Still don't have any parameters, but that's okay. That's okay. We don't need them yet. It's okay, right? This is A, this is B, this is C, and that's D, right? Yeah, Sean.
Just confused about the X1, X2, X3,
So remember, it's Y is equal to CX plus DU, right? X and U don't change. X is just my state variable, or my state vector, right? In this case, I've got X1, X2, X3, and X4.
Gotcha.
Keep my eye on the clock, so I make sure we have enough time for you guys to run through your points. Okay. Okay. Everybody good? We got any questions right now? Everybody, we cool? Because remember, we're gonna have to go into MATLAB with A, B, C, and D, right? That's what we want. That's what we're gonna get. We have to, obviously we need some parameters, right? We need some parameters to make this happen. And ask and you shall receive. Right? Here are the parameters. 50 kilogram driver. I mean, if this is for a commercial vehicle, I don't know any truck drivers who are 50 kilograms. Seems a little bit on the light side, but who am I to judge, really? The seat is 20 kilograms. We can investigate later, once we build our model, how changing the driver mass changes the vibration transmissibility we want, right? Okay. And all these numbers were pulled from a paper. They're not made up. Right? These are close to real values. These are experimental values that were taken from an actual study that was done. Okay. So there's a few things that we can do with a model here that we're going to talk about. Okay? A few things that we're going to do that we can talk about. There's a few situations that arise, right, because of we're in the real world, right? If you're driving your car, you're driving your truck, right? What are some of the things that can happen, right? Well, we can specifically talk first about an impulse response to this system, right? Speed bump or pop over, right? You're driving along, all of a sudden you hit a bump, right? Bicyclist, whatever it happens to be. Don't do that. That's bad junk. I apologize. So we can talk about the impulse response, right? So if we want to talk about the impulse response, right, this means that we're going to smack it with a force, and then the force is gone, right? So the force is there for 1 second, then it's gone, right? So that means that we were relying on the natural dynamics of the system to bring it back to rest, right? To bring it back to that initial condition. So it seems like it'd be a good idea for us to find the roots of the characteristic equation. Find the roots of the characteristic equation. Now this is a fourth order system, so we're going to have 4 roots. And Dr. D, you didn't plug in the numbers and tell us yet. We're just going to assume that you guys could plug in those values, right? And you would have the equation, right? Once we have the equation, what do we do? Well, there's actually an easier way of doing this, right, than you looking at the fourth order characteristic equation and sweating it, right? You didn't have a fancy calculator that'll do solving for you on the fly. You have both halves of the system segmented, right? You could get the characteristic equation for each of those second order systems and then factor them separately. Because the roots of the 2 halves should be the total roots of the system, right? So if we do that, right, and we could apply, you know, our fancy quadratic formula then, right? That guy. What do we get? We'll get 4 roots. One at negative 67, one at negative 7.3, and a complex conjugate pairing at negative 3.7 plus or minus 10.5. Sure. What we would get. So, here's a question. What type of response are we expecting given that we have those roots? What would we expect in this case? What would we expect the homogeneous solution to look like? Yeah, right. It's going to be stable, right? We know that from the negative real portion for all the roots. And we know that it's going to oscillate, and there's going to be some sort of damped oscillation accompanied with it, right? John. So that's what you need to find the, right, so if we go back, so what equations did we get the roots from, right? These 2 equations? You find the roots for these 2 equations, right? Where you've got just the M2, Z2, B2, Z2, right? That portion, find the roots for that portion, find the roots for the characteristic equation of the first system, right? So you got to find the characteristic equation for each half and then go after it. Right, because the input to mass 2 is technically Z.1 and Z1, right? So that should be on the other side of that's why it's equal there. So if you were to write a transfer function just for that particular mass, right, you would have Z2 over Z1 is equal to B2 S plus K2 over M2 S squared plus B2 S plus K2. Right, so essentially what you're going to do, the easy way, in my opinion, the easy way, well, all right, so in my opinion, the easy way is do it in your calculator, solve it equal to 0. If you don't have that option, the next way is create the characteristic equation for each half of your system and solve for the roots. Because we all know how to get second order roots, right? It's the quadratic formula. So here's our roots. The next question was, what do we expect the response to look like, right? And yes, that is, right? We expect it to be that, but specifically, we would expect right? Specifically, right, if we're doing give it the differential equations treatment, we would expect something of this nature. Okay, that's what we would expect. Based on that, here's another question. What is the dominant time constant? What was that, Danny? Is that the dominant time constant? Yes. It's 1 over 3.7, right? Because it's the slowest one. The slowest. Remember, the time constant, each one of these has a time constant, right? It's however long it takes for E to go to -1, right? Which signifies that our transient response has decayed by 36.8%. So we can find the dominant time constant. We can say that tau is equal to 1 over 3.7, which gives us a settling time of approximately 1 second. Like 4 times 4 over 3.7, around 1 second. Okay. So, why do we care? Right? Because this will be dominated by that damped sinusoid response, right? So that's what we're expecting to be most prevalent. Yes, there will be fast changes accompanying, right? There's going to be some initial transient dynamics that maybe don't look second order in nature, but overall, this system should look like a second order underdamped system when we look at the output, right? That's what we would expect. Oh, wrong one. And lastly, the last question for this slide. What are the natural frequency and the damping ratio? Right? What's the natural frequency and the damping ratio? Well, for that, we do need the root equation, right? We need the equation in standard form. Well, if we had gone through it and done it, right, this is the equation. Where is that equation coming from, right? This is the characteristic equation that gave us roots 3 and 4. Why did we decide to use that one? Because that's where the dominant time constant is. So, remember, in terms of simplifying our models from higher order systems, we know the responses to first and second order systems, right? We know the responses for first and second order systems. Everything that's higher order is a combination in some way of a first and second order dynamics, right? There's no such thing as a third order response. It's all a combination. So if we can find out what the dominant time constant is, we know which part of our system's dynamics is driving the bus. If we know that, like we found out here, this is the equation. Sorry, this should be 3.7. Right, this is the equation that gives us yes. So omega n 11.1, 11.2, round, whatever your rounding preference is, right? And we can solve for zeta. That was about 0.33. There it is, right? You know the natural frequency, you know the damping ratio. That comes from us investigating what is the dominant time constant, right? Now, what if what if this sinusoidal portion, this cosine function, had the 67 associated with it, right? What if? Well, then the dynamics would decay so quickly that you wouldn't even notice the oscillation. Okay. So now we do the simulant model, right? So we're talking about the impulse response, right? And typically in the past, how we've created an impulse has been we essentially game the step function, right? Because we don't use, there's no real impulse generator in simulant, at least that I like to use, right? So we typically just use our step function. We have it either start at a certain level and turn off after a very short amount of time, or you combine, you add a couple of them together, whatever you have to do. Right. So in this case, we need to generate our impulse, right? But instead of doing that, right, we're going to assume that our vehicle hits a bump that causes the sudden displacement of the cabin. Right? Speed bump, pothole, whatever it happens to be, we hit it. Right? We have sudden displacement, assuming we don't catch air, right? Assuming it's not like a Dukes of Hazzard situation, right? We should be all right. So how do we model this, right? Well, sure, you could do that impulse that we've been doing, but is that the most accurate way of us actually modeling an impulse? And it's not really, right? And so what we're going to do is we're going to talk about a triangular pulse. Right? So it's going to ramp up with some, you're forcing the ramp up, right? So when you hit this speed bump, you have certain amount of force, and that increases until we hit the top of the bump, and then it decreases on the way down. Okay, happens over a very short amount of time, right? So we're going to say that our peak displacement, right? So we're discussing essentially the profile of our impulse, or the profile of our speed bump, right? So the peak is going to be around 0.03 meters or 3 centimeters. The bump rate is 5.4 meters per second. Right? Since it's a triangle, we're just going to have it come down with the same rate, right? And we're going to say that this all happens over a very short amount of time. As defined by the maximum displacement divided by the bump rate. Okay. So the maximum displacement divided by the bump rate, which gives me 0.0056 seconds. Right? And so the total pulse is going to be twice this, because there's two sides to the triangle. There's two sides to the triangle. Okay. This is the part where I crashed the meeting with all of the simulants. Right? Please hold. Okay. We're almost to the good part, guys, promise. I'll share these files through Discord later if you guys want to play around with them. All right, so here's my seat triangle pulse code, right? You can see I have all my parameters entered. Yeah. I've got my I've got my A, B, C, and D matrices. I've got my initial conditions set as 0. Yeah. Right, I have my triangular pulse set up just the way we talked about. I've got the end time for my simulation as 3 seconds, right? So I'm gonna hit the bump, right? And then that's gonna be it. And so we're going to talk about, and I've got my my Simulink model here. Seat triangle pulse, right? So let me show you guys what that one looks like. Okay, so here is the seat triangle pulse model. So you can see, right, I've got the bump rate, right? So this is just on this left-hand side, this is just me making my triangle pulse, right? That's all it is. Right? And I add those three components together. What's going to come out of here is Z0 dot, right? That's going to punch out the velocity. I'm taking that and I'm putting that into a scope. I'm also going to integrate this, and that's going to give me, right, the position, Z naught. Both of those signals go into the MUX block, and those get fed into my state space representation of my model. That punches out Y, which is my outputs, right? And then I can plot them, which I will do using Simulink, but I also have a scope here where I've demuxed my signals, right? So I demux them, take the array of Y, and I split it into its output signals, and I can look at the scope there as well. Okay. So we go back. We're going to run this. Yep. That should, yeah, there you go. Okay, let's see. Uh-oh. Please don't freeze. Please don't freeze. All right, so what happened? Right? This happens. Please don't freeze.
Doctor, oh, there it is. Never mind.
Yeah. We were having technical issues for a second, but this time it worked out. I'm not so sure it will next time. Anyway, so here's the driver mass displacement versus time. So, right, you hit the bump, right? So that flat portion is telling us we're driving along. Remember, there was that flat portion. The flat portion of the input was saying we're driving along. It's flat, it's flat, it's flat for this long. Then we hit the bump, it goes up, comes down, and this is what we get out of it. So think about your experiences driving over speed bumps at high speeds, which you shouldn't do, but you know, it happens. You feel yourself go up and then come down into the seat, right? And then come up and so when I was working at BioRec, there was this accident I was working on. It was a low speed accident. Somebody had rear-ended somebody else and had a dash cam. It was a taxi driver, most taxis nowadays have dash cams. And there was an accident. He rear-ended somebody at a turnoff, and he wasn't wearing a seatbelt. And that looked way more violent than it actually was, given the speed that he was actually driving. But again, forward, back, right, up and down, right, and then you settle out. All right, what about the acceleration, right? Because that was something that we wanted to look at as well. So notice, like, we're only getting 1.5 millimeters, right? We're about 1.5 millimeters tops. We go into the seat about 0.5 millimeter. So not very much travel at all. But what about the acceleration? There's the acceleration. So we hit upwards of 6 meters per second squared for a tiny bump, right? So you have a large amount of acceleration relative to the size of the actual displacement input, right? What controls that? Well, the slope of the bump. Right, but then it drops off and it normalizes right here. Okay. So that's the impulse response. So let's talk about, and again, I'll share these files through Discord because LoudCloud doesn't like M files and similar things. So we can also talk about the sinusoidal response to this, right, at a given input, right? So this is the same, essentially the same code up to this point, right? And what this is going to do is it's going to ask you for an input frequency in hertz. It will do the conversion for you, right, before it puts it in the simulation. It asks you how long you want to run the simulation for, and then it'll run it and it'll export some plots for us, right? There's also a Simulink model that goes along with this. I can show you. So here's the Simulink model, right? So I've just got some sine wave input, right? That's going to give me my positional change. Right? I have to take the derivative of it to get the velocity input. I take both of those things, I mux them, I put them into my state space block. State space block, what comes out of it is y. In this case, you'll notice this says y is equal to z2, right? So we're only looking at the acceleration coming out of here, right? So I've altered my output equation to just discuss the driver acceleration, okay? So let's go back. And we'll run this one. Let's see what happens. So these are the standard parameters that we've been running. You can see, right, it's very easy for us to change them if we want to. But for right now, we'll run them as is. Wait for it. Oh, input the frequency. All right, what do you guys want to run it at? How many hertz?
144.
Okay, 144 hertz. How long? Well, 10 seconds. So. Okay. So.
I predicted nothing noticeable in the What's the amplitude?
Let me. Good question. What's the amplitude? It's 20 millimeters. Okay. So the plot's got two lines. One is a little bit harder to see than the other, right? But the floor is moving at 20, is an amplitude of 20 millimeters at 144 hertz, right, for 10 seconds. And notice the driver, you can kind of see it, has a dip down, right? So the seat gets pushed up into the driver, so it looks like the driver is moving down, right? Then he pops up and he settles. And you're back at it. Eventually, not noticing any of that, right? Eventually. Last year, somebody, I forget what the frequency was, somebody picked close to resonance and the whole thing exploded. Should probably remember what that is. But... Sure, you know what? Well, let's run it again. Here, if I do it in here, you guys will just see the change on the export on the plot. Yeah. So it overlaid everything, but the dashed line there, right? So what is this showing us, right? At lower frequencies, we attenuate less vibration. At higher frequencies, we attenuate more vibration, right? That was at about 3 hertz. I did use 2.7 as Danny suggested. Right, but you can see, right? So if we were to do a Bode diagram of this, right, we would expect that we would have some flat low frequency asymptote that's around 0 dB, right, to start with. It will likely spike up and then come down and start to attenuate. Okay, and then there's one last thing that we can talk about, and then I'll be done. It doesn't leave much time for questions. I apologize. Right? But this is my transmissibility code. Right? So you can see there's a bunch of different things. We can adjust all the K values if we want here, right? But it's the same model, right? Same model. Notice I'm only using y is equal to z2 is equal to x3. So I want the driver displacement. And this is going to plot my transmissibility versus my input frequency. Right? So essentially it's going to give us a Bodhi diagram, right? Hopefully. So let's run it. Let's run it and see. No. So it's still asking me for a frequency for the last one. I guess I hit run more than once. That's fine. Let me close it. Sorry, I didn't close any of my plots, and so it's doing super fun things. There we go. All right. So this is kind of like our transmissibility plot that we came up with earlier. We talked about earlier in class, right? My transmissibility is on the y-axis. My input frequency. So I've plotted the transmissibility only as a function of frequency, right? So if you wanted to make this beta, you could divide by the natural frequency of the system, right? You have transmissibility versus beta. And you can change all of your parameters in the code and see how that affects your transmissibility. But in this case, an input frequency of about a little over 1.5 hertz, right? Gives me the maximum transmissibility there. So 1.6 hertz gives me a transmissibility of 2.06. Right? So not really a big deal at small millimeters, right? 20 millimeters, you're almost an inch. I would argue that being shoved 2 inches up into your seatbelt's probably uncomfortable. I would say you probably don't want to do that. Right? But you can see, right? We plotted a Bodhi diagram though too, right? This is essentially what we would be getting out, right? You get the magnitude for all the frequencies. We could talk about phase too, right? Now I'll post all those in. Okay. There's one last thing. Oh, there's 2 last things. Okay. So let's talk about the physical representation of phase. Right. So similar to what we were just talking about, right? There's a wheel that's a suspension mechanism right, attached to the body of your car, right? And the wheel hits the road, right? And the road has got some sinusoidal input that gets put into it. So we understand magnitude, right? We say that, at a specific frequency, we understand what this is telling us, right? This is telling us how much vibration is being input, right? How much force and how much displacement is being transmitted through our system. Phase is interesting, okay? Because what this is essentially telling you is that well, first of all, I want you to notice that both the wheel and the chassis are about 90 degrees out of phase at all times. Okay? They're about 90 degrees out of phase at all times. What does that actually mean though? That means that if you were to put an upward displacement into the car, you will see a 90-degree shift in how that displacement behaves. It will not be transmitted straight up as it goes through. What is this like? You ever drive like super fast, like faster than you'd be willing to admit? I don't want anybody to get in trouble, right? So you don't have to incriminate yourselves, but we'll just assume that everybody has at some point or another driven their car so fast that it has started shaking side to side. You've input a frequency that is really, really high, okay? And you're getting out of plane vibrational dynamics, right? That's all I've got, guys. That's it. It's the whole semester wrapped up, done, bow on it. As usual, I have had a lot of fun teaching you guys. I appreciate you guys showing up. I know that this has been a strange semester with everything that has gone on with COVID and everything, and you know, it's just been weird. It's been weird. Thank you guys, and wish you all the best of luck on everything that's coming up. Sean. Yeah.
I guess just to be as prepared as possible for Thursday, what you should be trying and understand transmissibility, just what you went over the two problems, or
So, what should you know about transmissibility? Things that are important for you guys to know about transmissibility in the real world are, what does it mean? How does it affect your system? And how do you find it on a Bodhi diagram, and what does that tell you? Right? That's basically it, right? Understand how damping ratio and things affect it, right? But in the real world, right, if you ever come across transmissibility, right, and you may, depending on what you do, that plot that we showed at the beginning of class, being able to read and understand what that's telling you for various damping ratios is important. I mean, it's in the PE review book, guys, so probably important. Does anybody else have any other questions? We've got a few minutes.
Thanks for everything, Dr. D, for teaching.
No
Appreciate it.
No problemo.
It's been very helpful.
I'm glad. All right. Does anybody have any questions, like a quick one you want to go over for exam clarification or anything like that? Yeah, Sean.
for the benchmark, I know that we're supposed to choose three things that can be substituted in for tissue, but if you do the presentation, we can accelerate. If we pick like some abstract things and kind of like make them that way.
So for the benchmark, so for the paper, I'm fine with you choosing whatever you want, as long as you can find a reliable source to get material properties for it in your SolidWorks model, and you can appropriately discuss the economics of using such a material. Okay. Bless you. Outside of that, you can choose whatever you like. You don't have to, since you're a biomedical engineer, right, you're probably a little bit more well versed with what is actually used as a biomedical material, right? The only constraints are that, you know, the body won't reject it, and that, you know, it's not like, so adamantium and vibranium are probably off the table, guys. Just throw that one out there. As much as I would love for them to be real, unfortunately not. Yeah. All right. Any other questions? No? All right. So here's the real reason you guys came to class today then. All right. Here you go. There's a link in the chat in Zoom if you want to do it that way. You guys will get 30 minutes, right? It'll be self-timed. The Laplace transform table and the master sheet are linked, just like the last exam, right? You're going to need your student ID number to get in. If it's not working, please shoot me a private message in the chat, and I'll see what I can do. So I'll post it again because if you just joined the meeting, then you're not going to see it. But it's also up there. Remember, cameras on your workspace, please. Or